In this video, I want to write a program to read a character from the keyboard and then determine whether the input character is uppercase, lowercase, or etc. So as you can see, I declare some prompts and messages for the output messages. I insert a \n in the front of each message in order to display it in the beginning of a new line. First I display the inter-character prompt for the user, and then by using system call number 12. We can read a character from the keyboard and the ASCII code of the input character will be saved inside the sign with 0. Now I want to check the input character and determine is it an uppercase character or not. As you know, the condition that I want to check in high-level language like C can be written in this way. Assume that the input character is inside C variable. If the input character ASCII code is greater than the first uppercase character uppercase A and the input character ASCII code is less than or equal, the last character in the uppercase range is Z. Then we should print something like this. How we can implement this complex statement in the MIPS assembly? First we should check the complement of this condition, so I can write it in this way. If the input character is less than a so branch less than 4 unsigned number, if the input character which is inside the sign with 0 is less than the first capital letter or capital A, go to the next one. But if it is greater or equal to the character A, we will reach to the line 19. Now take the reverse of this condition. If it is greater than that, it doesn't belong to this interval. So we should go to the next one. So branch is greater than 4, unsigned, but outside with 0. And the last character in this entire world. So when we reach through line 20, it means that both of these two conditions are not satisfied. So in fact, the input character is between A and Z. So by this way, we can implement the logical end of two statements or two conditions. So here we should print that the input character is uppercase. So by using this system call, I can do it. Let me copy, paste it. Third, the name of the variable. And don't forget to jump to the end of the program and ignore or skip the statements. So the health of this statement is next one. Or if we reach to the next one, it means that the input character is not belongs to the capital or uppercase interval. Now we should check it for the lowercase. And the lowercase is exactly the same as the uppercase. Only I have to change the lower and upper band of the interval with lowercase a and lowercase that. And instead of next one, go to the another label next to and here instead of capital the lower. You take the name of the Bible as lowercase. OK. Lowercase. And here, when we reach to the next two, it means that the input character is not belongs to the capital or lowercase. So I will print another message and say that this character is something, etc. For this purpose, I have a message that I declared and name it as other. Oh, this is an evil statement. First, if it's here and if it is blanks to A to Z, we will print this as this message and skip the other else part. Otherwise, in the else of this statement we have another. If it is between A to Z, we will print lowercase and skip the other part. And finally, this is the health of this. If and if the input character is not belongs to capital or lowercase, we can print that the character is other character. Let me run it. The first. Save it. The antique symbol not found. Don't forget to declare your end label. OK. Input the character. For example, capital T. Message uppercase correctly displayed. Reset it. Run it again. Lowercase s. The lowercase. Correct. And take it for something else, for example, 7. 7 consider has other types of characters. And everyone. And welcome back. In this video series, I want to solve some of the midterm questions. In the first question, I ask you to write a MIPS program that asks the user to enter an integer and then displays the number of zeros in the binary representation of that integer number. For example, if the user enters 24, then the program should display 3 because we have 3 0. In binary notation of 24. This is the binary rotation of 224,11,000. So the number of zeros in this binary notation is 3. I declare two messages here. Enter an integer and the number of zeros equal to this number. These are not automated strings. Now, by system call number 4, I display their prompt 1 message, and then by system call number 5, I read one integer number from the keyboard and store it in color. Sign temporary registers 0. And then I want to count the number of zeros for this purpose. This is my algorithm. Let's assume that we have a number that we always hear. For example, number 24, 11, 0. 425 make it? What's up with you? Changing to keep the fight. Now I end this number with this value. Number 1. So by this way, all of the beats in the original number becomes 0 because n of 0 and everything will be 0. Only the first beat will be remained. Maybe it is 0 in the original number. Maybe it is 1. In this example, it is 1. So now I have this value. And if this number is 1, it means that the first beat is not 0 and it is 1. So since I want to count the number of zeros in this case, I don't need to increment the content. But if after and this number is 0, 1, the answer becomes 0. It means that the first digit is 0. So I will increase the content for in this case. Now, after I check the first beat, I have to do the same thing for the next one instead of change the one here. I shift the original number 1 unit to the right. So this will be the result after shifting. Now again, I am these two numbers, and this time the answer becomes 0. So since the answer is 0, it means that the second beat of the original number was 0. So I count. This is one time again. I shift this number to the right. This is shift to the right. Again. And this number and again, the answer will be 0. So this is the second time. So I increase the counter from 1 to 2. I repeat this operation. Shift to the right. And then this time the arm will be worn. So it means that the third bit is 1. So I don't think to increase the counter. I will shift the original number one time again to the right. I will repeat this shifting to the right until the original number becomes 1, when the original number becomes 1. It means that there isn't any other zeros in the original number. And this is the last bit. So I should stop the procedure or algorithm and the counter shows the number of zeros in the original number. In this example, 2 because 25 only consists of 2 zeros. So as you can see, this is the counter balance 91 and this is my original number, the last 3 0. Branch equal this number 1 1. If they are equal go to the end otherwise and the t0 and 1 and store it in a temporary just 30. To check it. Is it 1 or not? If it is 1. So it means that the corresponding bit is 1 and we don't want to count it. So we come to this loop 2. Otherwise we increment the quantity 1 by 1 unit. Anyway, then we come to the loop 2. We have to shift logical to the right one time and we come back and jump back to the loop 1 later. When we exit from this loop, the result is inside the register. T1 I want to print it. So first I display this message by the system call and then the value of the 3-1 will be moved to the sign a 0 and by using system call number 1, we print an integer on the screen F3 and 524. The number of 0 is 3 or 1024. Or to cover 10. It consists of 10 zeros. 4. 255. Its consists stop 8 1 so there isn't any 0 in there 255.